Relative motion. There are a few definitions we need to discuss before we start talking about relative motion. First of all, we need to talk about frames of reference. When two objects are moving relative to one object, the other object is moving. Let's say, for example, you're standing on the side of the road and you see a car that's going south. Now, relative to you, the occupants in that car are moving south. However, if you're inside the car and you're looking out at the person on the side of the road, since the car is moving south, relative to you, you would see the person moving north. So we have to talk, first of all, whose frame of reference are we referring to when we start talking about motion? Two different frames of reference can see two different events. For example, the person inside the car would see the person outside the car moving north, and the person outside the car sees the person inside the car moving south. We also have this example of a tennis ball being dropped while walking. If you think about a person who is dropping a tennis ball while they're walking, the person who is walking would see that tennis ball just fall right beside their body while they're still walking. However, from the outside perspective, you would see that ball have a horizontal velocity while it's falling at the same time. An example of this is kind of like when an object is dropped out of a plane. Relative to the person in the plane, that object falls straight downward because both you and the object have a horizontal velocity. So they're both moving horizontally at the same rate while the object falls. However, if you're on the outside of this looking at it, you would see that object falling, but it also has a horizontal velocity, so it actually follows a curved path. That curved path would be a parabola. So as it has its horizontal velocity, it accelerates downward, forming a parabolic path. That's different than what the person inside the plane sees. They just see the object moving straight downward, while you see the object moving in a parabola. So let's talk about a boat that's moving across the river. Now with this boat, it has to move this direction. It has to point to the northeast, and the reason it has to do that is in order to go straight across the river, it's got to have part of its velocity in the direction against the river's current. The current is flowing to the west. So the boat needs to point east and north at the same time. The eastward component, what's called the component of the vector, the velocity vector, has to balance out the velocity of the river. Alright, so the boat's velocity relative to the water is going to be to the northeast. The water's velocity relative to the shore is going to be west. So after I add these two together, I'm going to get a resultant of the boat relative to the shore. Now this is not taking two numbers and adding together like we do with scalars. You take 2 plus 3 and you get 5. This is going to be with respect to each other, and they're going to be vectors. With vectors, since they have a direction, then it's not just simply adding the numbers together. You have to break the vectors into components, and we'll talk about that more later. But you can see here with the northward and eastward components of the velocity, the eastward component is going to be balanced by the westward current of the river, and the resultant is going to go straight across. Now the entire time the boat's not facing to the north, it's facing to the northeast, but it's going north. So relative to the shore, the boat will be moving north even though it's pointed to the northeast. So we come to this problem. Suppose a boat is moving upstream at 20 meters per second relative to the water, and the current is 10 meters per second relative to the shore. So how long will it take the boat to go 500 meters upstream and then back downstream? Well, we have to ask two questions. While it's going upstream, how fast is it going? Well, if it's going 20 meters per second relative to the water, and the water is moving 10 meters per second relative to the shore, to go against the current, that's 20 meters per second minus 10 meters per second, which gives you a total of 10 meters per second for the boat relative to the shore. What about coming back downstream? Well, this time the boat is going in the same direction as the current. So 20 meters per second plus 10 meters per second gives us 30 meters per second when it comes back downstream. So we got two parts of this problem. While the boat is going against the current, then we have 20 minus 10, because 20 meters per second relative to the water minus 10 meters per second go in the opposite direction for the water relative to the shore, then the boat's only going 10 meters per second while going relative to the shore. If you think about a person on a treadmill is moving forward at a certain velocity, but the treadmill itself is going back at that same velocity. So relative to the person's surroundings, the person's not moving at all, even though he is moving by walking on the treadmill. It's the same process here. The boat is going against the current, so the current's kind of pulling it back while it's trying to move forward. So in order to figure out how much time this takes, we take velocity and the displacement divided by velocity, because displacement equals velocity times time for constant motion. So displacement divided by velocity gives me time of 50 seconds. If we look at the second part, while it's going back downstream, then this time the current is going with the boat. So it's 20 plus 10, which is going to be 30 meters per second. We take the same displacement, which is 500 meters, so it went 500 meters upstream and then 500 meters back downstream. 500 divided by 30, and that gives us 16.7 seconds. The total time for the trip is going to be 66.7 seconds. Now, if we didn't have a current at all, and they were going 20 meters per second upstream with no current, if you take 500 divided by 20, that's going to be 25 seconds. 25 seconds upstream, 25 seconds downstream, the total trip would have been 50 seconds. So you see, with a current, it takes more time to make a round trip than it would without a current. So we have two train tracks that intersect at a right angle. Train station A is 155 kilometers north of the intersection, and train station B is 110 kilometers east of the intersection. So the question is, what is A's displacement relative to B? Well, if we think about this, in order to get from B to A, we have to go 110 kilometers west to get to the intersection, and then 155 kilometers north to get to A. So in order to figure out the total displacement, we have to figure out the hypotenuse as well as the angle. To figure out the hypotenuse, we're going to take the Pythagorean theorem, take the square root of 155 squared plus 110 squared, and we get 190 kilometers. The angle, to find the angle, we're going to do inverse tangent of opposite over adjacent. The opposite is 155, the adjacent is 110. Divide those and then take the inverse tangent of that, and your calculator gives you 54.6 degrees. And we know it's going to be north of west because this angle right here is north of the direction of west. So the next question is, if we have a train that's leaving from train station A going south at 44.6 kilometers per hour at 2 p.m., and then a train leaving from train station B going west at 37 kilometers per hour, leaving at 2:30, will they collide? Well, I wouldn't ask this problem if I didn't have them collide. It wouldn't be interesting otherwise. So really the question is, what time will they collide? Well, if you take the total displacement for train A, it's 155 kilometers moving at 44.6 kilometers per hour. If you remember that the amount of time is going to be the displacement divided by the velocity. If you take 155 divided by 44.6, you get about 3.48 hours, about 3.5 hours. Add that to 2 p.m. and you get 5:30 in the afternoon. Train B, if you take the 110 kilometers that they travel divided by 37 kilometers per hour, then you get about 2.97. So you get about, about 3 hours added to 2:30. That gives you about 5:30 in the afternoon also. So about 5:30, these are going to collide. If you're more exact, you get 5:28, and one would be 23 seconds, the other would be 31 seconds. And I've really never seen a train pass an intersection in 8 seconds, so they're definitely going to collide. Here we have a video of a plane that's trying to come in with a nasty little crosswind. You can see that the plane is kind of angled off to the side. It's not pointed its nose directly at the runway because there's a crosswind that's pushing against it. In order for it to line up, it's got to actually point into the wind a little bit as well as down with the runway itself. Now as it's going down, you can see that it's pointed off to the right here while it's going with the runway. And in order to keep in line with the runway, he has to point not only down the runway but off to the right as well. And as he goes through, you can see that when he tries to line up his nose with the runway, he'll actually get pushed off to the left. Keeping his alignment with the runway, he has to tilt off to the left, and then when he actually has to turn his nose in order to land, the wind kind of carries and picks up one side of the plane, which allows him to, or doesn't allow him to actually land. So he throttles up right here. That smoke right there is actually from the engines pushing off in order for him to take off and go around and try it again. Alright, so now we have a plane that's flying north with an indicated speed relative to the air around it of 80 meters per second. there is a wind blowing at 20 meters per second toward 60 degrees south of west. Now, with that being said, the 80 meters per second is relative to the air, the plane's velocity relative to the air, and then 20 meters per second, 60 degrees south of west is the velocity of the air relative to the ground. So we need to figure out the plane's velocity relative to the ground. And like before, we would add these two together, but we don't just add the numbers to get 100, we have to add them like vectors. So we have the plane's velocity, which is 80 meters per second north, and then we have the wind's velocity, which is 20 meters per second, 60 degrees south of west. Now you can see that this vector, this 20 meters per second, is going to have a west component and a south component. Now the west component is going to blow the plane off course. The south component is going to go against the 80 meters per second. So we have to figure out what each component is. For the x direction, it's going to be 20 cosine of 60 because it's adjacent to the 60-degree angle, which gives us 10 meters per second. And then the y direction is 20 sine of 60 because it's opposite, which is 17.3 meters per second. So that means the 80 meters per second subtracting 17.3 meters per second gives us a total of 62.7 meters per second north. So it slows it down, but it also has 10 meters per second that it's blowing it off course. So if the resultant velocity is 10 meters per second to the west and then 62.7 meters per second north, you can see that the resultant is going to be up this way at this angle. Now if we use Pythagorean theorem, 10 squared plus 62.7 squared and then square root that, we get our velocity, and then we take the inverse tangent of opposite over adjacent, so it's 62.7 divided by 10, we get our angle. So the velocity is going to be 63.5 meters per second at 80.9 degrees north of west. And you can see that angle is going to be north of west.